Hi, everybody. My name is Sebastian. And today I'm going to talk about our recent ICMA paper that I have together with Valentin, my supervisor, Ulrike von Luxburg, and Subash. And the title of the paper is How Much Can We Forget About Data Contamination? Okay, so I have 10 minutes and I want to do two things. And I want to pitch the main results from the paper so that you guys get a bit an overview of what we did there. And I also want to try to embed it a bit into, okay, why is this research question interesting? And what's the general context, right? Okay, and first about me, I'm a postdoc in the group of Ulrike von Luxburg. I did my PhD mostly on explainable machine learning. And recently, like many of us, I've become interested in large language models. Okay, and I am currently very interested in pre-training. Okay, unlike most of you here who work on post-training and benchmarks. So this is a paper about benchmarks, but you can also read it about a paper that is just about the question, how much do individual samples actually matter during pre-training, right? Sort of we are going to look at this only for benchmark questions and from this perspective of benchmark contamination. And by benchmark contamination, I mean, I have some benchmark question and I evaluate the model sort of on this text string. And during training, at some point, the model has seen exactly this test string that I evaluated on during pre-training. Okay, sort of I will consider this sort of exact form of contamination. And the question will be, how much does it actually matter for the final evaluation if you've seen this data point, this text string at some point during pre-training? Okay. And okay, a bit in general, what am I interested in is this question, how does pre-training work, right? I mean, what aspects of the optimizer, the architecture, and the training data, of course, contribute to the fact that at the end of the day, we get such an amazing model, right? That can do so many things. And what sort of effects are going on during this pre-training? Okay. And if you're interested in this, feel free to reach out to me after this talk or anytime. Okay, now to the particular project about data contamination. So we all know it's a well-known in machine learning, data contamination can lead to benchmark overfitting, right? We all know that there are various ways in which you can overfit the test set. Okay, but if you sort of train a language model in a realistic performance setup, how much does it actually matter, right? In a quantifiable sense. And I don't have time to go into this in this talk, but there are all sorts of reasons why you may believe that if you train even a big model on a really large amount of data, that individual samples actually don't matter so much for the final. Okay. And what I want to do is I want to run really controlled experiments, okay, where I train language models of different size, with different number of model parameters on data sets of different size. And then I just insert the benchmark questions at different rates into the training data. And at the end of the day, I measure what was the causal effect of this. Okay. And of course, this is related to this general problem that I already talked about. Okay. And for some reason, I mean, you can't read the title. The title is Data Contamination Exhibits Scaling Behavior. Okay. I can move this away. Oh, thanks. Thank you. Okay. Right. So as you may know, LLM pre-training is a lot about scaling, right? And sort of we are now also going to look at the question of data contamination from a perspective of scaling, okay? And we are going to consider scaling along 3 different dimensions. The first dimension of scaling is the number of model parameters that the model has. The second dimension of scaling is the number of tokens that we train the model on. And the third dimension of scaling is depicted in the different colors. How often are the different benchmark questions repeated in the training data? Okay, for example, if we look here on this plot on the left-hand side, and sort of I consider this ceteris paribus, sort of I keep everything else constant and I scale 1 dimension, okay? And sort of the first plot depicts the effect of scaling the number of model parameters, keeping the size of the training data constant. Okay, and so for example, here for this small model, 124 million parameters, if we repeat the benchmark questions 12 times into the training data, then we get an accuracy increase. And I always measure the difference in the accuracy between the benchmark questions that I've inserted into the training data and sort of IID set of benchmark questions that I didn't insert into the training data, right? And so here sort of the effect of this would be 10 percentage points. right, of this 12 times repetition. And then we can see if we increase the number of model parameters, sort of for all contamination rates, sort of like the causal effect of the contamination increases as we increase the model size, right? Sort of like the effect of contamination is more severe for larger models. Okay. And this may be expected. But interestingly, there also exists like a second countervailing effect. And this effect is depicted here. Okay. Here we keep the number of model parameters constant and like insertion times, and we increase the number, like the size of the training data set. And like we measure the size of the training data set in Chinchilla tokens. And for those of you who like know the Chinchilla scaling laws, this is like a number of tokens that corresponds like to the model parameters by the factor 20x. Okay. And sort of here what we see is if we increase the size of the training data, then sort of the effect of the contamination is actually monotonically decreasing. Okay. And this goes up to the point where if we train a model on 15 times the Chinchilla amount of tokens, which is actually like the setting for many of the popular LLMs, at least for the LLMs for which we know. But for example, for the Llama models and for the Lllama models, they would be roughly here in terms of the Chinchilla token. And we see that like even 12 times of contamination, I mean, it's like slightly larger, maybe 1 percentage point, but like the confidence interval overlaps here with the whole of, right? So here we see that like it's, I mean, of course, I didn't train a really big model here, right? But for the model that I could train, which is like maybe the best proxy for a realistic training setup, actually like even 12 times of contamination don't have like a huge causal effect on the final model performance, right? Okay. And then, of course, we can also look at like different scaling dimensions, but I'm going to skip this in the interest of time. Sort of then what we did in the paper is we sort of looked more closely at like what is the reason that when you scale the size of the data set, that the effect of contamination becomes smaller, okay? And it turns out there's actually like this established effect in deep learning and also like in LLM pre-training, which is called forgetting, okay? And forgetting means that if you see something at some point during pre-training, and then you continue training without seeing it again, right? Then you sort of increasingly like the effect of the samples that you saw before on the final model, it decreases, okay? And sort of in this experiment here, we show that if at a very particular point during pre-training, we heavily overfit the model on the benchmark questions, okay? And then we continue pre-training and don't show the model the benchmark questions again. If we continue pre-training for long enough, okay, that is here like at this point, then all the accuracy differences from the overfitting are gone, okay? Sort of like, then you have like the same accuracies as if you had never seen the benchmark questions before. Okay. And then what's also nice, sort of this forgetting, it can also be demonstrated like in other models. Like these forgetting experiments, they don't require as many tokens as training from scratch. So we can take an intermediate model checkpoint, for example, from the Olmo models where it's freely available. We can sort of insert the benchmark questions, and then we get like a huge overfitting effect. And then we can continue pre-training, and then we sort of see these forgetting curves. Right. And now one last result, which is very cool, I think, which is my favorite result of this paper, which is like the scaling of these forgetting curves in terms of the model parameters and the number of tokens. Okay, sort of what do we see here? We see here two curves that look like exactly the same. Like the first curve is the forgetting curve for almost 1B. And the second is like the forgetting curve for almost 7. But if you look closely, like what is very different is like the number of steps on the x-axis. So here, like the Olmo 1B model, it has like, after essentially 4,000 steps, it has almost completely forgotten the contamination. But for the 7B model, it takes much longer. So even after 20,000 steps of training, there is still like a significant difference in terms of the contamination, right? Okay, and now what we can do is we can sort of put these two curves on the same axis, and we sort of scale the number of tokens that the model sees in accordance with the number of model parameters, okay? And then what we see is that the forgetting curves of the two models overlap really nice. Okay, and what does it mean? Intuitively, it means sort of if you sort of double the number of model parameters, like a model that is like twice as big needs to see twice as many tokens in order to exhibit sort of the same forgetting effect, right? So at least like, so I talk a lot about scaling, like we didn't properly estimate any scaling laws in this paper, right? Because we just ran out of time. But at least for like these two different models, we see like this really nice scaling effect. Okay. Now, main takeaways. Okay. The impact of data contamination exhibits scaling behavior. I showed you this. And I would also argue, and we have some more arguments on this in the paper, that many like real world training setups are actually fairly robust to at least like moderate amounts of sort of this form of data contamination. And the mechanism for this is example forgetting. And also interesting, and this is a bit more general, like a lot of effects in LLM pre-training, they exhibit this spiky then forgotten dynamic. Okay, which means that immediately after you see something, some sample or some data, and this has also been shown for other types of data, like the model usually reacts to this, right? Sort of like the model like is hugely sensitive to the data seen during the last gradient steps. But then if you sort of continue training, this effect also decays super quickly. So that if you don't see things again during pre-training, then like it just doesn't matter. Okay, and if you see things sort of repeatedly, then you have like an effect where you see something, you forget, but you don't completely forget, and then you see it again, and then at some point you start to remember it. Yeah. Okay. And now, of course, there are like a lot of open questions, right? I mean, we only did like this one very controlled, very specific experiment with benchmark questions, okay? There are a lot of questions like, would it be different for other kinds of data, right? We could also ask, you know, like these benchmark, this effect, like, in a sense, what I showed here is like very different to privacy questions, right? Because privacy is also about this question. You see something, can you at the end of the day detect that your model was trained on this, right? But in privacy, it's usually about lower bounds, and everything that I showed here, this was all like overall on average results, right? So it's like, there's like a lot of open stuff, and yeah, but I think I'm already at the time. So thanks for your attention, and I'm happy to take any questions.